Hi everyone, thank you for coming back to my talk. Eunice, you want to say anything today? No? Okay, good. So thank you for being back here today. The focus will be again in big data, but there will be a small discontinuity. I won't be showing you too many neural networks or discussing ethics today, but I will be talking about how logic can deal or cannot deal with big data, what can be done and what cannot be done. And the main subject of today is the consequences of a result in complexity theory. So I'm not talking about complexity theory, just the results of the consequences of it. Okay? So I'll start saying, well, what are the advantages of logic with respect to big data? So big data is a problem with logic. Most people just ignore, no, I don't want to pay attention. These people just hand wave. Okay, talking about hand waving, I'll hand wave so much today, don't be surprised if I take off and start flying around. And then I'll talk about what logic is good for, and maybe we can do that, use that for big data. And then we start where, let's face the complexity of logics and try to find tractable logics. There are many around. They are not very nice. They are kind of more or less ad hoc. We try to do less ad hoc than they are, but they are not as beautiful as you would have it, like classical logic with Boolean algebra and multivariate logics with Lukashevich logics with the NV algebras, etc. But we'll talk about both today. And then one thing that people talk about is logic should be used for explanation, because these deep learning machines or programs, they are very black box in the sense that we don't know what they are, we don't know what they do, they just do, they learn something, they don't tell you what they've learned, and then they perform well or not well, and you don't have a good idea. So maybe we can use logic to explain what they may do. And I'll try to give you an idea, a project that I have going on in that line, and then I'll conclude. Okay? So again, please interrupt me anytime for any reason whatsoever. If you find mistakes here, please counterexample, etc. So the disadvantages of logic with respect to big data. Okay? So logic is complex, and it's not complex in the sense that it's hard to understand. It's complex in the sense that it's hard to compute, independently of who is computing. Most basic logics, like propositional classical logic, is empty-complete already. So it's in the gray zone of tractability. And this is the main point, really, to deal with big data. If you want big data, you want efficiency, and logic is not efficient. It's expressive, and you pay a price. So formulas are rarely good explanations. So if you want to explain what's going on with a formula, I just asked what that magic formula was doing, and well, it does some magic. And this is kind of a general phenomena. Logic is not so easy to understand. You need to explain logic. So if you propose to explain something with something that must be explained, well, you haven't reached there, wherever there is. Okay? And then there are many logics. So which logic are you going to use to explain something? So there is an uncountable number of logics, potentially. So depending how you define it. But some people say most of them are rubbish. I'm not doing that at the moment. There is a potentially very large number of logics. So how do you deal with that? And even if you find one, say first order logic, which signature? What are the predicates? Their rarity, etc. It's not immediately obvious. But what's the language? Okay. And when we try, oh, let's learn, I'm learning sets of rules in whatever logic you choose. That's clumsy. That's also very hard. Not as easy as those stupid neural networks. You cannot use the video cards, the GPUs for learning in logic. You need more than sums and multiplications for doing that. And the logics are not modular. This is also a big problem. So when you have a big logic, you take one axiom, you add one axiom, what's the impact? It can be huge or it can be small, and our intuitions are not very good. I'm not sure if I change something here, if it's going to affect some other place. Logics are not modular. So let's go to the first problem I mentioned, complexity. So complexity theory, in my opinion, is one of the greatest contributions of computer science to human thought. Well, that's not to take it easy, but because of complexity theory, we now know that some things are complex, not because I cannot solve, it's not complex to me. They are complex because there is no easy solution for them. Okay, so complexity theory allows us to say about complexity per se, not complexity in relation to me or to you or to whoever. The problem is complex, not it's complex with respect to an observer. Well, it's also the fact that computer science was invented, or Turing machines were invented, as a side effect of proving the undecidability of first-order logic. So computer science was born by when you found a limit to computation. To find the limit for computation, you must define what's the computation. Okay, and then maybe we should try to implement, as von Neumann said, try to implement Turing's universal machine, and that's the idea of the computer. Okay, so so it was born already with a very high complexity problem in mind, undecidability, which today is considered equivalent to non-computability by the Church-Turing thesis. Okay? And then when you think of a simple logic, philosophers say, even proven logic, that very simple thing, it's very complex. It's already NP complete. So what's considered simple in terms of expressivity is already too complex for computer science and for big data. Because people I want a more expressive logic. I want to be able to express this, that, continuity, blah, blah, blah. But they have to pay a price for it. Computer science is a mirror image of the world. You cannot get anything for free. If you want more expressivity, you need to pay for it. Complexity, with taking more time to reach a solution, if there is a solution. And then let's consider logic as an explanation tool. So it's not very good. Well, is a small theory a good explanation? Even one axiom, a single formula in a context is hard to explain. It looks magic. If you ever given a class of logic, you write down a formula and say, this formula means that, there's always some student, why? Please explain that to me. Because it's not immediate, it's hard, it's coded, deeply coded meaning in a formula in terms of explanation. And if you have a huge problem, you will demand a huge theory, a very large number of formulas. Is that a good explanation? Are you better served with a huge theory than you were with your black box system in the first place? It's not clear that explaining through formula, people say, logic is something that you can understand what's going on. Maybe it's faster, but it's not that easy. It's still far away from a good explanation in many senses. So So if you try to explain a single formula to a student, and when I wrote that, I didn't know we were discussing the continuity axiom. But look how hard it may be. And the formulas, they interact. So you should say, well, this formula has a meaning or has an explanation in the context of all these others. You take one of the context, maybe the explanation changes. So it's not really obvious how the things interact. So if you plan to explain something using logic, maybe you're not giving a very good explanation for most people. Maybe someone will be pleased, but many people will say, well, it didn't clarify to me. You just translated Sanskrit to Urdu. I don't speak any of these languages, sorry. No, if you speak Sanskrit or Urdu, I don't mean any offense, okay? Just the language, I don't know. Anyway, and if you want to deal with big data, you need computational tools. I need computational tools. That's what I do, computer science, okay? And well, there are many tractable logics around. If you take a logic that expresses a little bit more than propositional logic, it extends propositional logic, any model, temporal, description logics, blah, blah. They already, that extends propositional logic, they inherit the complexity, and probably they shoot the complexity up sometimes until undecidability. And there are infinite levels of undecidable already. So we are almost all the time looking at the abyss in terms of computational complexity. With logics, we are very near to the abyss all the time. If you want to have a tractable logic, you have to prune the logic, throw away something, find a fragment or some way of forbidding that tractable logic to do things that you have in, say, basic propositional logic in order to attain tractability. And even what people say, oh, it's polynomial times. It's a polynomial of times of degree 6. It's very efficient. What? Not for big data. For big data, quadratic is already unbearable. Okay, so this thing that tractable is polynomial is a convention, and anyone in the front line would say, well, it's a very bad convention. For big data, you need almost linearity. You want to read the data once or a few times, which we call epochs, by the way. And that's it. I want to read, say, 20 times. That's linear in terms of complexity, or almost linear. Don't want to keep going back and forth with the input data. Don't have time. My life is too short. I have to pay for the cloud computing system for the amount of time I use it. So I don't want to spend too much money. So there is this tractability is also not that tractable. It's just a convention. And where are the logics of near linear complexity? I don't know many. I know a couple, they're pretty useless. Maybe, I don't know how to use them. That's a possibility. We have nice logics that are linear, and I think it's too poor, but that's because I don't know how to use them. Or anyone so far doesn't know how to use them. Okay. Now, what logic is good for? Okay, don't want you logicians to commit suicide now. Okay, so logic is good for proving things. And can you prove things about a neural network just by looking at the neural network? Very hard. But we can use logic to do that. And today I'll talk to you one way I dreamed about and how to do that. Use the Lukashevich logic. Okay? Like, if you want to prove the properties that people prove of programs in general, like safety and liveness. Safety means I don't want to reach a dead end. I don't want to reach a situation where that's bad. There are bad situations. Like I don't want to be ever in a bad situation. I prove a safety property. I have to define what it means to be bad, and I can prove that that formula is never reachable. Okay? And liveness is the opposite. Liveness means there is a good state, and I'll always come back to that good state infinitely often. So when you type something and you hit enter, in some time in the future you go back to the prompt again and get something back. This is the idea of liveness and safety. Can you do that to a neural network? And we have proven some properties like that for neural networks. So far it's a bit complex to do that, but we're moving towards that direction. It's possible, okay? Or to approximate an approximation of a neural network, I should say. Just a second. Okay? Can a process be controlled using a neural network? Can I use it in a plant? Because software is used everywhere to control valves and places, etc. Can you use intelligent neural network software to control processes? No one has done that so far. Neural networks, I said yesterday, work in an open environment, no closed loop. So just get the data, train it, and then apply it. No, and control is closed loop. So we don't know how to do that. Maybe logic can help us. I still don't know how to do that. I have some projects and people want to do that, but they want to look at the result of the neural network, and then some people go there and do something. Or an alarm sounds, and some people do something. That's the way of controlling, putting the human in the loop. The human closes the loop. It's possible. Use shouldn't despise human this much. So okay, so let's try to face complexity. Let's look at the tractable logics that there are so far. I'll start with the very basic ones, the one should know about. Fragments of classical logic. Okay, we have well-known fragments of propositional classical logic, or even of first-order classical logic that are tractable. Okay. Well, that's supposed to be propositional fragments. And probabilistic fragments, there are the fragments of probabilistic logic. It's funny, there are many funny things, like both of these logics, the propositional logic and probabilistic logic, they are NP complete. But probabilistic logic is harder than classical logic. Come on, Marcelo, you're being contradictory now. You said both of them are NP complete and one of them is more complex. And it shows here. You have to prove more things out of probabilistic logic in order to bring it to tractability than you have to prove from propositional fragment. Example. Suppose you have two-clause logic. So it's a two-sub problem. You have lots of clauses with at most two variables. This is tractable. Easy to see. Easy to provide an algorithm that solves this satisfiability problem. Okay? Now try to do the same with probabilistic logic. Take two clauses and give probabilities to the formula, and can you say that this whole set of probabilistic assignment is consistent? This problem is already NP complete. Okay, so what's going on? What's going on is that the class of NP problems has internal structure. And within that structure, there are problems that are more complex than the others. If you know the definition of NP completeness, you require that there is a reduction from one problem to the other that's polynomial. but the polynomial that does the reduction may be a polynomial of high degree. If you have a polynomial of degree 0 or the polynomial of degree 3, the second one is more complex than the original problem in the reduction. So there is internal structure in the NP class. That's what's happening here. And SAT, Boolean logic satisfiability, classical Boolean satisfiability, is one of the lowest levels of that complexity. Not the lowest, but one of the most useful. So when you want to solve an NP-complete problem, first thing you reduce it to SAT and then use SAT machinery, which has been developed very well in the past 20 years or so. And you compile a problem to SAT and use a SAT solver to solve that problem. That's one of the most immediate ways of solving an NP-complete problem. Sometimes you blow up the problem quadratically, cubically, depending on the kind of reduction you have. Okay, so whereas I have been able to solve SAT problems of millions of variables, 9 million variables in less than an hour in a computer. So this means that if you have a cubic reduction, you can only solve a problem of 100 variables because you get 1 million in, so 100 to the power of 3 is 1 million. So you can do that, but be aware that this reduction, this so-called efficient tractable reduction, is not that efficient, and tractable is just a convention. And in probabilistic logic, there are probabilistic fragments. Graphical logic means you can only have rules with one antecedent and one consequent. That's it. It's called graphical because it looks like a graph. You have an arrow from one to the other. That's why I call it graphical logic. And probabilistic graphic logic is tractable. Then there are modal, temporal, and description logic fragments. Saying people from description logic, they love the EL family. That's fantastic, tractable, and very unstable. Anything you add to it, it blows. It blows, but doesn't blow to NP complete. It becomes P-space complete. Anything you add. I mean, it's so in the limit of tractability. That's not me, that's Franz Bader saying that. Okay? So we say don't mess very much with EL, you're gonna end up badly. You add probabilities to EL, you become what was non-deterministic exponential space. Yeah? Not inventing this result. It's there in the literature. Okay, so tractability is maybe delicate. And then there is a huge class of approximation of classical logics. And that's why I brought Renata here, because we started with that. Or we developed that. And there is a sequence of logic that approximates classical logic. And each logic is tractable. And then you move to the next one, and to the next one. Hey, wait a minute, you're going to prove that P is equal to NP. No, because the amount of steps that you may get in there is exponential. So this is approximation of classical logic. I'll talk to you soon about it. And approximation, not of fuzzy logic, sorry, no. Vukoshevich logic, okay? I didn't write fuzzy, sorry, it was a mistake. Because it's a new result from last year. Okay. So, tractable propositional fragments. There are 3 very well-known tractable propositional fragments. First, propositional Horn clauses. What are clauses? Disjunctions of literals, of variables and their negation. In a Horn clause, you can have at most one positive literal, one non-negative literal. This is a Horn clause. And you have a set of those, it's tractable. Actually, it's so tractable, it's P-complete. If you mess with a little bit with it, it's explode. Wait, horrible slide, who wrote that? Then you have two clauses I already mentioned. A set of clauses with just two literals. They may be both positive, both negative, don't care. And then it's not P-complete, it's just a log space complete. What's the difference? No one knows. It's one of these, R is equal, R is the same, can one simulate the other? No one knows. Right? And then you have XOR clauses. Clauses that instead of disjunctly use exclusive OR. This is just like solving a linear system. And this is, I don't have a completeness class, which means they are more efficient and they are, of course, less expressive. These are three famous fragments that can be solved with algorithms in polynomial time. Very well known. Horn clause is actually very efficient. There are very efficient algorithms. Anyway, okay, and Horn clauses are rules, so people love them. The restriction to two variables, they seems very kind of unintuitive. Why two? What's there in two? But Horn clauses are rules, so I can understand it, or can try to understand it. Anyway, so these are the famous. You can find proofs for this almost anywhere. Just Google it, and you'll find it. Or come to my classes. I show this result. Okay. Then there are tractable. The idea of tractable approximations. They were originally proposed by Scherf and Cadoli in 1995. What's the idea? You have a set of parameters that grows. You start with the empty set, put a propositional letter inside, put another one, put another one. Every time you add a propositional letter, you're adding a parameter to your logic. You'll be approximating classical logic when you do that. How? They proposed two ways, two logics that operate only on clausal level. Okay? I haven't dealt with this logic for a long time, but S3 is a logic that allows three possibilities. When you have P and not P, they can be 0, 1, 1, 0, like in classical logic, and they can be also 1, 1. That's why it's called S3. There are three possibilities for a pair of complementary literals. Okay? And if you have this kind of semantics, they have no proof theory. If you have this kind of semantics, you have a logic that's tractable. If you add one element here, now this element is a variable that doesn't allow for this non-classical valuation. So you're adding classicality to the variables in your language. You say, well, when I add one propositional letter here, that propositional letter does not accept this valuation anymore. It must be 0, 1 or 1, 0. And of course, if you add all the propositional letters you end up in classical propositional logic. Well, no, here. You end up in classical propositional logic. No. Come on. Oh, sorry. You end up in classical propositional logic because you put all the variables inside. Okay? And so what's the property? If you prove a theorem in S3 empty, it would be a classical theorem. It would be a theorem in every step of this approximation. But if you have a formula that's not a theorem there, well, maybe it becomes a theorem in when you add, say, you force seven propositional letters to be treated classically. That's what happens. And this logic you may try to understand. The other approximation is very odd. It's called S1 with small letter. And you have super theorems. I mean, wait a minute, before you freak out. I know that classical logic is maximal. So if you add one extra theorem to classical logic and you close it under the proper operations, it becomes inconsistent. This logic is not inconsistent because we don't close it under anything. Okay, we just add. And basically, when there is nothing inside the parameter set, the empty set, everything is false. P and not P are both false by decree. Okay, that's the only valuation I accept. And then there are rules that propagate to clauses the usual way. So when you have no elements here in the parameter set, all clauses are false, independently of what you write in the clause. Because all literals will be false, the disjunction of false is false, the conjunction of false is false, and then you have the semantics of false. Once you start adding things, and that's, well, once you start adding things and things becomes falsifiable in this logic, it will be falsifiable in classical logic. So here we have theorems that if they are proven in the approximation, they become theorems of classical logic. Here is the dual. You have falsifiable formulas. If they are falsifiable in any of the approximations, they are falsifiable in classical logic. We have these two kinds of approximations. Okay? So the number of approximation steps may be large. Okay, well, this is kind of very ad hoc thing. There comes Renata, showed me this thing, and then we worked together on general approximations. The first one we now call approximations from below. It means that you start with the logic, and all the theorems of that logic, they are theorems of the next one, and of the next one, and of the next one, until you reach classical logic. And there are approximations from above. And now the parameter can be anything, not just propositional symbols. It can be formulas, it can be something else, like in depth-bounded Boolean logic, which is a depth that's used as a parameter. So we described and gave several examples of logics that approximate classical logic from below and from above. Okay? Most usual, well, what we understand mostly is approximations from below. Approximations from above, that you have a logic that, a set of formula that will be inconsistent, but it's very hard to think about these things. Very unintuitive. Once we start doing that, we kind of lose the ground. Wow, what's happening? There's no intuitions evaporate very easily, right? And I think you don't work with this for a decade. No. So I can see. So here each step is incremental and tractable, but the number of steps may be exponential. Otherwise, I have shown P equals NP and break all the codes in banks and etc. The police will be after me. We have shown several logics that has both proof theory and semantics. Tableau methods, other methods, semantics for each of these approximating logics according to the parameters. So it became an industry. And then came a philosopher with a very nice idea. Say, well, this is not very well motivated. Let's motivate an approximation. And this is depth-bounded Boolean logic by D'Agostino with me and Lógica. And his motivation was very philosophical. He said, oh, natural deduction is too intuitionistic. That's not how a classical person thinks with the right? Are there many students of D'Agostino here? One or two? Remember? Yeah. Here, that was his motivation, right?
He presented his
Yeah.
research project
Oh.
before yesterday.
But I'm talking about you in front of me. Okay? So the starting point is what's called the pure intelligence, introduction and elimination rules. And he said, well, I remember so many things I don't want to say. In natural deduction, you have to hypothesize things. Forget about hypothesis. Just take the pure introduction and pure elimination without any hypothesis. Like you want to prove an implication, you hypothesize A goes back to B, then you discharge A and prove A implies B. Okay? Though this rule is not allowed in the first step. Okay? Then you have a linear decidable logic, because, well, all the proofs are linear. But in that logic, there are no theorems. So there is no formula that you can prove from nothing, because you have to hypothesize something. So there are no theorems, but you still have a deduction relation. So if you get some hypothesis, you can reach some conclusions. So there is a consequence relation, but no theorems in the first level. And then say, instead of hypothesizing, I'll do something that's more classical. I'll use a principle of bivalence. So either A is false or A is true. So then you can branch, and then, well, there are ways of using this rule forwardly and backwardly. But once you have used the principle of bivalence, you left the first level. Every time you want to hypothesize, you move one level up. And you want to hypothesize twice in a branch, there is the depth bounded, the depth of the deduction, you have moved two steps. Yes, please?
Sorry, I didn't catch this. Could you explain why you think, or the authors think that natural deduction is somehow intuitionistic? Could you explain why?
So this is a philosopher's natural deduction is totally intuitionistic.
Why?
In classical logic, how do you reason about a disjunction? What's the classical reasoning with disjunction is sometimes called syllogism. You have A or B, okay? And then you say A is false, therefore B. That's a classical way of thinking about the disjunction. That's not at all the way intuitionists.
Actually, like when we think, like what's more intuitive in a sense, there have been done a lot of psychological investigations that show that in natural deduction we have the rule of disjunction elimination, and that is really an intuitive rule. That's how we reason when we reason with disjunction, which is like, which is a natural deduction rule. And also,
because intuitionism has to do with constructivism, but it's not classical.
It doesn't have to. It doesn't necessarily have to. But I agree with you that you're somewhat right in the sense that natural deduction is more. The system is more beautiful.
I didn't say that natural deduction is bad. I just said that the rules of natural deduction, they are based on intuitionistic logic, in the intuitionistic way of seeing the world. That's a general philosophical criticism of natural deduction. Have you ever tried to prove in natural deduction, or anything, A or not A? Have you ever tried to prove that? How many lines? 8, 9. Have to hypothesize. You start by hypothesizing its negation. It's a big mess.
But you can also have, what you're saying is that you want.
If you want to have that as an axiom, then you try to prove elimination of double negation. It's the same mess.
So you're saying that you want all this to be primitive, right?
To be, well, that reasoning of proving in natural deduction A or not A, or elimination of double negation, it's not at all trivial. It's very hard, actually. When I show students, they normally give up my course. They go to the swimming pool.
Of course, I mean,
You can either choose, you can either have elimination of double negation of, but if you have one to prove the other is a big mess.
This would be a primitive, would be an axiom.
Yeah, the rules will be more classically oriented, like this. Getting this should be easy because that's classical. But it's not. Try to do that in natural deduction. Do it now, just as an example. You see, it won't come up easily. Yep.
If I understood right, the point is that, okay, it may be difficult or easy, but when you talk about intuitionistic logic, you cannot prove some things. So
Yeah.
it's weaker than classical logic. And what you're calling intuitionistic here, so you have the,
Yeah, have the double quotes.
it's like, it's just a way, but it's not really intuitionistic because natural deduction is complete.
Yeah. Right. If you have the appropriate the argument is that you don't reason classically, and the whole point is about how do you reason classically. Yeah. Reasoning classically and reasoning intuitionistically, they are very different things. There is the one branch of mathematics, constructive mathematics, in which people only allow proofs that are intuitionistic in a way. Reason intuitionistically in the proof. You have only constructive proofs.
Can I say something? No, because I find your point very interesting, but probably connected with natural deduction. I don't think that, I mean, we can have a version of natural deduction that is classical, and actually Marcelo, Gabai,
Yeah.
they have given natural deduction rules, but that mimic classical reasoning, not intuitionistic.
Yeah, it can be done.
But that's what you are looking for, right? Because you have some.
I just wanted to know like why, because I didn't see like immediately why like natural deduction is not like classical system of natural deduction is not classical. That's why I wanted to like because okay.
But Jensen's natural deduction employs intuitionistic reasoning. That's why. That's the philosophical criticism. And then he said, this idea of hypothesizing is what makes complexity high. That was his point. And he said, well, if I control the amount of hypothetical reason that I allow, then maybe I can approximate classical logic in a tractable way, and that's the case. Okay, that's what we showed in that paper. Actually, there was an original paper just by D'Agostino in which it showed this logic with the semantics, and then we showed that it could be used to approximate classical logic. Okay, so his motivations were philosophical on the way Jensen's system. I think it's NK. Jensen's system NK was classical logic done in an intuitionistic way. It was very similar to system NJ. If I say something, I don't have all these things in my head all the time. That's correct. So this was the motivation for this kind of reasoning. So this is an approximation with a philosophical motivation. That's all. If you think it's classical, well, we can do classic logic, of course. Anyway, let me go. So one can approximate classical logic this way by controlling the amount of hypothesizing of things that you don't know if it's true or false, and then adding it in a limited way. In all these logics, there are algorithms that are tractable for solving that. Of course, every time you move from one to the other, the exponent increases. Okay? So here is, I think it's quadratic, and here is already to the fourth power, and here is to the sixth power, if I'm not mistaken. I didn't check this. We've done that 10 years ago. And then, well, they're not very good for computing. They may have interesting philosophical motivations, but not very good for computing. And then we did that for Lukashevich logic. And it's crazy, but it's nice, at least for me. Okay? What have we done? So Lukashevich's infinitely valued logic. Why? Because I like it. I need it. It's the right logic for what I want to do. Okay? I'll explain it later. Sorry, Daniela, I'm using your logic. So you prove the beautiful results, and I just go there and hack it.
Go on.
Thank you. Thank you. We have a satisfiability reasoning based on linear algebra. How do we do that? We introduce a new variable psi I for each subformula. So suppose we have a set of formulas. We want to say this formula has truth value 1, the other one has truth value 4, the other one has truth value 0, or 4, no, 0.4, sorry. Okay? And then you want to see if there is a valuation that satisfies all that. Okay? It's a decision problem. So how do we do? For each new variable, we introduce a parameter psi I for each of the subformulas that appear in the original formula. Okay? And for this, it comes from the semantics. Okay? And in order to decide that logic, you have to guess a value for each of these psi I, 0 or 1. Once you've guessed, you solve a linear system, and the solution of the linear system is the solution of the original satisfiability problem. Okay? So if the problem is unsolvable, it means that the formula is unsatisfiable. If the problem is solvable, it means it's satisfiable. Just like that. And then you can see immediately that the problem is NP complete, because you know what to guess. You have to guess disk size. If you guess it correctly, you have a witness, and then you solve in polynomial time a linear system, and then you have it. And that's the witness for the satisfiability or unsatisfiability. No, unsatisfiability. That's the witness for satisfiability. If you cannot solve it, then it's unsatisfiable. Okay, so what have we done? We have relaxed this system. Instead of 0, 1, now you can assume a value in the interval 0, 1. And what happens is that the semantics of formulas of the whole set becomes not a valuation, but becomes a polynomial, a polyhedron. That's why I call this polyhedral semantics. Once you relax these extra hidden variables, the semantics is not a single point in an n-dimensional space. It's a polyhedron in an n-dimensional space. And I won't tell you what n is because it's hard, but anyway. And the fact is that, well, if you have this polyhedron, decidability for that logic is tractable. It's just solving a linear system, which is tractable. Okay? And then how do you move from one system to the other? You guess what's here. You choose a few ones, you guess. You keep guessing until you reach here. And it's an approximation from below, because you have proved unsatisfiability of the system here, then it's unsatisfiable in the Lukashevich infinite logic. If it's satisfiable here, maybe it will be unsatisfiable someplace else. So you keep adding these guesses. Of course, in the end, in order to show satisfiability, you may have to try all the number of guesses is exponential, because you have, I guess, 0 or 1, 0 and 1. This is basically a tree. Yes?
Typically, how many, in which dimension, how many variables consider infinitely many.
No, we have to consider one guess for each subformula that's present in the original formula. So it's a linear algebra trick that we do, that whenever we have a max or a min, we add a new 0-1 Boolean formula, Boolean variable, that represent, and you get to represent that semantics that you know that in Lukashevich, if you have a valuation, those formulas will be either 0 or 1. And that can be shown. It's easy. I mean, it sounds complicated, but if you know the basic tricks of linear algebra, that's easy. So that's how we do that approximation. So, and it's an approximation from below. So remember, a theorem here, we don't deal with theorems, but we deal with unsatisfiable formulas, which is the same, becomes a theorem here, which is, so it looks like an approximation from below. So why did I decide to approximate Lukashevich many-valued logics? This is actually joint work with Sandro Preto, an ex-student of mine, and Felipe Magna from Barcelona. Because we want to use it to prove properties about neural networks. Okay, how do you prove properties about neural networks? Well, wait just a second. I'll try to explain that. I'll be hand-waving a lot. I may take off. So let's try say if you want to give an explanation in terms of you want to induce rules to explain something, what's going on. So basically you have a conjunction of premises and you want to prove that implies some concept. But I don't think this is a good explanation, because if you're dealing with neural networks, the input for a neural network is the intensity of a pixel. So you get explanations on the intensity of pixels proving something. That's not an explanation for me. I mean, it's just making my life harder. I don't want to, when I look at you, I don't see pixels, I see you. Okay? I see faces, beard, or ponytail, or t-shirt, whatever. I don't see pixels. And if you apply this kind of rule to a neural network, if you induce rules based on its input is a sequence of pixels for an image. Imagine for voice. What's the input? I didn't tell you yesterday. What's the input? There are three possibilities. You can take the intensity of the wave, the sound. Rubbish. We don't go very far away. We do Fourier transforms. Yeah. And then you take a spectrum and do a spectrogram. You do every 100 milliseconds, keep on. That's more or less for human voice. If I'd done just that, I would have lost 10% of my precision. We do a second transformation that didn't exist when I was a student. I had to study about it. You take kind of the whole of the spectrum. It's called an MFCC or a cepstrum. I didn't invent this name. Okay, so you have frequency, and in the cepstrum you have differency. I didn't invent this name. Sorry, you can be angry. I was angry. It's stupid names. Okay, but no matter what the names, this is much better when we use this MFCC transform to identify properties of a voice. We get 10% improved, which is a lot. Imagine if you have 80% precision. When you move to 90%, you've thrown away half of the mistakes. You have improved 50% in the mistakes that you made. So, okay. So imagine if you have inputs, points in a differency, intensities of differency, and you provide a rule like that. What does that mean? I have no intuition on that. I know it works, but I have no intuition on that. So Can we make logic useful for explaining? These rules are not explaining much. I mean, they're just making life harder. Okay. So, I'm calling this explanation by proxy prediction. Suppose I have a neural network. I want to explain or to predict properties of that neural network. A neural network, and that can be proven, is a continuous function. There is no discontinuity in sums and multiplications and the exponentials, etc. Sometimes you have it. We may not have derivatives calculated in all points, but only finitely many points in any case, and they are always continuous. Okay, so I can try to approximate. How do you approximate a function? With what? With another function that I know how to deal with, a piecewise linear function. So, okay, this is what I approximate a continuous function. I can always use a piecewise linear function to approximate a continuous function. This is Weierstrass, or modification of Weierstrass, right? So I approximate the continuous function with a piecewise linear function. And then what I do, I transform this piecewise linear function into a formula of some logic. What? Classical logic? No. Classical logic has only 0 and 1. Cannot. Has nothing in between. I need a logic in which it is easy to approximate a piecewise linear function. To reason about this piecewise linear function, which is representing the neural network. Okay? Many problems in the middle, but that's the idea. Well, we have to try something somewhere. When I had this idea, I thought, oh, I'm a genius. And then I found out that people had already thought about it 20 years before. It has happened several times in my life. I had a brilliant idea, then I found out that someone had a better idea than I. Many years before. Okay. I get depressed and then I get happy. Okay? I get depressed because I'm not that original. Big deal. Who cares? And I get happy because I'm not that crazy. But someone has already thought about it.
Welcome to the club.
Okay. So we can approximate the neural network by a formula and demonstrate properties about it. And this idea was developed by Amato and many others in the 2000s. So when I thought about it in the late 2010s, well, I just reinventing the wheel. Okay, the wheel is useful. But these people had very, very complex logics to deal with. Even Danieli had a logic to deal with this problem in 2002 or something like this. So the logics used were too expressive and therefore too complex. So what's going on here? So Vukošević is closely related to piecewise linear logic. Suppose you have a formula in Vukošević piecewise linear in Vukošević infinitely varied logic. The set of all valuations for a given formula is a piecewise linear function with integer coefficients. That's very easy to show. What's hard to show is McNaughton's result. 51. Sorry. I have to fix many things in the slide. So McNaughton showed that the reverse is also true. Whenever you have a piecewise linear function, then there is, with integer coefficients, it's called a McNaughton function, for a reason, then there is a formula in Vukošević infinitely varied linear logic whose defining function is exactly that one. So it's kind of complete. It's a completion result. Okay, and that's very interesting. But I'm annoyed by integer coefficients. I don't want to deal only with integer coefficients. When I approximate a continuous function, I want to use any coefficient I want. Okay? So how do you move from integer coefficients to rational coefficients, which is called a rational McNaughton function? there are many ways. Amato and they used a logic called L/L pi half, which is can represent all the roots of polynomials with that. It's very expressive, and of course it's too hard. Then Daniele added an existential quantifier. How do you call that logic?
I didn't give a name.
Okay, so that's why I don't remember. Good that I don't remember. So it's the existent Lukashevich, which is nice. It's sigma 2p complexity. It's above NP. It's one level higher in the polynomial hierarchy if you know complexity theory. If you don't know, well, it's a little bit more complex than
Daniele and Aguzzoni.
Aguzzoni. Okay, Daniele and Aguzzoni. Okay, but I didn't write, just talking to you. Okay.
Aguzzoli.
Aguzzoli. Aguzzoli, thank you. And then Sandro and myself, we showed that we can do that staying in Lukashevich linear logic with a pair of formulas. Okay, take a pair of formulas and such that the first one, the capital one, it's a set of formulas that you want to make with value 1. So remember these valuations can go from 0 to 1. We fix these formulas with 1. Then when you restrict to this set of valuations, the values that you get for phi is a piecewise linear function with rational coefficients. That's the trick. We represent with a pair of formulas. And then we proved the other way around, which was much easier to prove than the original McNaughton result, which was horrible. Then Daniele proved in a much better way, but you have to just shoulder heads and whatever. We don't need any of that. It's simpler here, at least in my opinion. So Sandro showed that for every linear function with rational coefficients f, there are pair phi and big phi, such that the corresponding function is f. You can always do that. And we have a linear time, polynomial time algorithm that builds this. You give me you give me f, and I build the pair of formulas in polynomial time.
Marcelo,
Yes.
is this a localization theorem? You localize the initial function to some special domain where the coefficient of
Yeah, well, we built this formula at the same time that we built the other one, and then in the end we take maximum and minimums of everything goes together. That's the idea of the proof. Okay. That's due to Sandro. I gave him the theorem and he proved it. Okay, that's what I suppose supervisors do. So this construction has been used to demonstrate several properties by proxy of neural networks, which we are able to have a neural network, we approximate it by some piecewise linear function, then we compute a huge formula that doesn't mean anything, but then we can use that huge formula and the inference mechanism of Lukashevich's satisfiability to show liveness and safety properties of that function. So we prove things by proxy. Of course, this last part is still NP-complete. Reasoning in Lukashevich's infinite values logics is still NP-complete. That's why we want to approximate it. Okay? So that's the whole story. And that's it. So conclusions. Well, big data poses big challenges to logic. Most people try to look away. No, big data, bad thing. Oh, forget that everyone is talking about it, okay? I'm not talking about it. I'm the world. But, well, we don't do that. And we say, well, logic can be used for what logic can be used, which is proving properties about neural networks. Suppose you have, there is the famous accident in which there was a car, driverless car with a neural network going on a street with a certain speed, and then something that it was never trained for happened. You know, one of these huge lorries came out and it was in front of the car, white. And the neural network didn't recognize it as an obstacle. It thought, oh, it's just the sky. Crashed into the lorry, and the person who was inside died. Okay, that was not the first, not the last time these things happen. With humans driving cars, it happens all the time. Anyway, but you would like to prove properties about this neural network if you're going to stay inside playing cards while the car goes from São Paulo to Campinas, as I've been doing all these days. So, well, seems an interesting path to pursue. Okay, there is some reasons for doing that. We still need low complexity logics and better algorithms to do, but we've shown that there are ideas that we can explore in this stuff. Okay, thank you. That's all. Questions? Yes.
So what's the real role of Lukashevich in your work? Because it could be using, for instance, this BL logic as Larry mentioned today, logic.
Does it have all these properties that you mentioned? Continuity is there? It doesn't, because that's the only logic that has all these properties. The Lukashevich is the right logic to represent piecewise linear functions. And that,
Because of McNaughton.
yes, McNaughton property is I'm choosing that logic because of McNaughton property. Okay, it's not that I don't have shares of Lukashevich logic that I get if I use it. No, it's just the right logic. Yeah, I didn't buy it. No, I was looking for something, and that's the right property. Okay, that's why I chose it.
I will do this tomorrow in the last lecture. We do McNaughton with some mathematical detail.
Okay, thank you.
Like it's Peirce and so on, but it can be taught.
Good, excellent. It's the right logic for this, at least for me. Okay, and we have a better one with the right properties of swap.
There is no other one which enjoys McNaughton.
Yeah, that's right. And I was annoyed by the integer coefficients. That's why we moved a little bit further. Yes, please.
It might be a silly question.
No.
I want to know about what these days AI can implement logic and what cannot in itself. When I use ChatGPT in these days, I mostly test it can understand, it can distinguish between some invariant argument, valid argument, but it mostly fails. So my question is, the future AI can distinguish between, when we give them some kind of test, it can verify or distinguish between some arguments are correct or some arguments are valid.
That's $1 billion question. Yeah.
Please repeat.
Yeah, he was asking something that's more related to yesterday's talk, but he said, ChatGPT is not doing things that are very smart. They can fool you, but they do not no relationship with truth, right? Can we improve that? And I'm saying that's $1 billion bet. Microsoft thinks it can. It's putting $10 billion into that, according to the New York Times. Okay? Even that, can we prove properties about ChatGPT? Because now we can test properties, okay? You can have an empirical way of checking, don't like this. Can we prove that it doesn't have, or it won't go? Can we prove that a driverless car won't go to some well-known problems, or you can prove in general that it will be safe? We need some way to formalize it. I am proposing, actually people have proposed that, but well before these techniques have been developed, an idea of how this can be done. Okay? ChatGPT has lots of problems. People are thinking of suing OpenAI for giving them bad advice, but they have this warning, oh, use it as you wish. If you don't like the results, that's not my problem. That's what Google has been doing all since it began. So it's using the same strategy.
Could you explain why it is difficult for such an AI? Because
I can explain why it is difficult for ChatGPT, because I told you, it is trained to generate text that looks like text. It's not trained to generate text that's true, that's useful, that's good, that has been proven to be used in any particular domain. Okay? It's just a huge effort to train a software program to generate text that looks like human text. That's how it's trained. Okay? And so it doesn't generalize. It generates text that looks like text and it's full of rubbish. Today, I saw a blog today that say, tell me about the Gödel's theorem. Oh, it has been shown a wrong result. And it was corrected, blah, 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 this and that. It was all false. It was all generated by ChatGPT. So it invented a different history of the discovery of incompleteness of arithmetic. Generated by ChatGPT just because he wanted. And you can get inconsistencies in it. But it's trained to generate, well, that's very impressive that it can generate this kind of fake news. That's what it does. And
I think you touched the point here. So when you see big data poses a big challenge to logic, I think we can sell the use of logic for things like proving the properties about the system. So you don't want an autonomous car to be proving theorems.
No, I don't want autonomous car to be proving theorems. No.
But before you launch a big product, you may spend like 3 days waiting for an answer.
How is it going to react to a lorry or something like that? Or mud in the lens of the camera, or a child running after a ball or whatever like that. Yeah, if you can formalize that, it's hard, very hard. Anyway. Yes, please.
Quite understand how you relate the continuous functions with the piecewise approximation of the system.
How I relate. I'll show you the theorem or the idea of the hand waving, but suppose you have a continuous function. Okay? I'll change color. This is a piecewise linear function. Oh, I don't like this one. It's too okay. No, I like to do that. Oh, I can do that even closer. That's the approximation. You can always get closer and closer to the original one by adding extra points of inflection.
Okay, but my following question is how proving things about these pieces relate to safety or liveness constraints? Like,
Safety of liveness constraints are formulas of certain form, shape. So we can use, you can translate them to Lukashevich linear infinitely meant value logics and prove them. So, and they represent some safety. So I don't want to reach a state with which I can see a white thing and not stop. I want to show that. So I want to show that whenever I have something very suspectful, the car will reduce its speed. Okay, and never go to in a speed higher than say 50 kilometers per hour in one situation. I can prove that. Okay, this is a safety problem. Liveness is that the car will always stop, so it won't be going on and on and on and on without stopping. Eventually, it will stop, and I can compute the period of stopping.
for instance, if we're talking about autonomous cars, the y-axis would be like the acceleration, and the x-axis would be like other variables.
I don't know. It can be complex. Who said it's simple to model this situation? I didn't. can be complex modeling. You may need an expert on how to formulate the properties. Absolutely. It's not for anyone. It's hard to formulate formulas that are good. Okay, maybe even an industrial secret. What formulas you prove to guarantee safety? Okay. Yes.
Because about how far do you think we can go with proving these properties? Because I think in the older expert systems, like we had these very abstract spaces in which do traditional mathematics and traditional logic. And traditionally, like we have integers that help with flow and things like that, and we have systems that control it that we show equivalence to our abstract constructs. And now we have the AI that can do things that are much more impressive, doing things that we could not do, but we are not too sure. It's not like in the expert system that we knew they were going to do it right, because we had constrained in a certain way. Now we don't know how we're going to do it right.
I'll tell you what I think. I'm not very good at doing predictions, so I won't do a prediction. How far can we go? I think that if people see value in these things, they will push much, much further than where we are. This is kind of an initial step, an idea that someone had 20 years ago and didn't go far because, well, there was no interest. But if there is interest, renewed interest, and money in, available for that things, people can go much further than that, if they see value in it. That's what I say. I don't think this is the latest shout about it. That this can be much more developed. Okay? But I'm not very good at all in predicting things. If you told me 10 years ago that we would be having ChatGPT like this, I said, oh, hey, come on. Because that ChatGPT solves Turing problem in many cases. And I was totally skeptic about it, but I was wrong again. Yes?
What are the difficulties of this approach phase?
Sorry?
The main difficulties.
Oh, it takes some time. It's not like something that you put the formula there, press a button and look at the answer. Sometimes you have to wait hours, days. But that's also for training neural networks. Days of training, weeks of training. And what happens if in the end you find out there was a bug? You kill yourself. Students working with this, they suffer a lot. Okay? It happens all the time. So it's
The students
suffer, and yeah, the supervisor suffers together. Okay? Yeah, it happens all the time, but it's weeks sometimes. I say, well, if you do your work well, you can go to the beach while the computer is working, and you come back and check the brilliant results. Okay? Yes.
Do you consider networks that like currency, like feedback, right, and have temporal interaction?
Speak louder, please.
If you're thinking about neural networks that have recurrency, and like dealing with the problems is like temporal postulates. Does it complicate your how you gonna prove these properties?
Oh,
This dynamical.
this proof ignores completely the structure of the neural network. The idea of having a piecewise linear function is irrespective of what's the structure of the neural network. Of course, if you want to prove what's called a time series processing, it's a bit harder than just one input and one output. But this method totally ignores how you obtain the original continuous function. If it was a neural network or if you just draw it in the board, who cares? So it's independent from that structure. That's what you asked. Yes. And we don't know yet how to do its time sequence, but we're going to get there. Yes.
I'm curious about the proof theory of these your approximations to recursiveness.
Yeah.
You have proof theory for that?
No.
Ah.
No. We have a satisfiability decision procedure which is based on linear algebra. That's all I have. Okay, no proof theory. Okay, but I have an algorithm which is good enough for me.
So is there any way to introduce a rule that avoid risks? I'm saying, because you are working inside a certain parameter between 0 and 1, but sometimes, as the example you used with the car, that, I am seeing a blank wall, but it's not the sky, so...
The problem is not seeing the blank wall, the problem is seeing the blank wall and not stopping the car. That's the problem.
But is there any way to, because when you put a product in the market, for example, maybe you have to introduce some security rules inside the algorithm to avoid certain complication. I don't know if there is a way to measure that.
I will cite myself when I'm teaching first-year students on how to program. I say there are many ways to make a program right and infinitely many to make it wrong. So I don't think you can harness all risks, because the risks evolve, they change all the time. There is infinitely many or uncountably many risks that can appear. So, well, I think there will always be trouble. We're never totally safe away from trouble. Traveling in airplanes is pretty safe these days, but sometimes an airplane falls, disappears.
So
it's low probability, it's safe enough for people to trust, but it's never risk-free. Okay, anything, going up an elevator is never risk-free. And that's the safest medium of transport we have. It's measured. Okay.
But maybe some kind of risk, a degree of risk avoidance.
Yeah, if you can harness, yes, yeah. You can reduce it to an acceptable level. Defining what the acceptable is hard, but people say, oh, that's good enough for me. And they be doing that with airplanes and elevators. So, yes.
This means that we are doing classification and the classes are discrete. How do you do that?
That's easier for me. Yeah, it's not very much different than that, because when, remember that we have, this is all many-valued. So you can transform any set of numbers into numbers between 0 and 1. And it looks like a probability distribution. So it could be 1/4, oh sorry, no, this would be 3/4, this would be 1/5, and this is what's left. Okay? You can transform that. So when you have, if you have 3 categories, you say category 1 has this probability, category 2 has this probability, category 3 has this probability, and I choose this one because it's the largest. That's how we classify things. And this is used all the time. Of course, this is not really a probability distribution. I have not proved that it generalizes to a state, if you have been following the previous course. Okay? It's a fake probability distribution. It looks like, but just in the numbers, it's not. Because we have no conjunction, disjunction. I don't even know what's a conjunction here. So I cannot generalize it to a state.
Okay. I think you could
Okay. Yeah. Maybe. Tomorrow we'll be debating, telling stories and debating, finishing those problems.